Alright everyone, it's Mr. Riddy back with yet another video. Today guys, we're going to be discussing our final topic in Unit 7, which is on solubility equilibria. And before we begin, I would like to remind you that we have discussed the solubilities rules prior in the school year. In Unit 3, we looked at the solubility rules through a lens of intermolecular forces. And just very briefly, generally speaking, right, if you had an ionic compound composed of highly charged ions that had small atomic radii, this had a high force of attraction, and we tended to say that that was likely to be insoluble in aqueous solution. Then we looked at the solubility rules again when we were predicting precipitation reactions. And you'll recall this is where we took the molecular equation. We wrote the complete ionic equation to determine the ions that remained aqueous throughout. Those, of course, were our spectator ions. They were also soluble, right? And then we talked about the ions that were forming an insoluble solid called a precipitate. Those would be our insoluble ones, right? Well, in those units, we presented, or rather I presented solubility as you're either soluble or you're insoluble. And now that we have equilibrium under our belt, I can tell you, well, that's not really true. So in this section, what we're going to be investigating is just how soluble is a particular ionic compound, okay? So that leads us to our equilibrium that is on the page here. We have calcium fluoride solid is in equilibrium with calcium 2 plus ion, which is aqueous, plus 2 fluoride ions, which are also aqueous. The equilibrium constant for this particular equilibrium is 1.46 times 10 to the negative 10th. And folks, this is the process of what we would say dissolution, which simply means that how much of my calcium fluoride salt, okay, can actually dissolve in this solution. And that's where we establish the equilibrium. Now, we interpret the equilibrium constant the same way we would as if we were looking at a Kc or a Kp. So that's to say that this is a much smaller than 0 for our equilibrium constant here, which means, guys, that the reverse reaction is favored. If the reverse reaction is favored, right, then we know that calcium fluoride solid is going to be favored in this reaction. And that's all suffice it to say that this salt, very, very little of this salt actually dissolves, and most of it remains as that precipitate, that insoluble solid. Okay. Now, we use a new equilibrium constant called the solubility product constant, KSP, to measure this. And again, similar to K's prior, right? Similar to KP and KC. It's going to tell us the degree in which, or rather, where this equilibrium lies, okay? Except when we're saying, well, where does this equilibrium lie? Does this mean that this insoluble solid is very much that, insoluble? Or is calcium fluoride very soluble? In this case, we saw it was insoluble. Okay, so some common KSP values are included on the sheet here. You'll notice that most of these are from our solubility rules, right? That are the compounds that were in fact insoluble and with their respective KSPs. You'll notice that all the KSPs are less than 1 because according to the solubility rules, they were in fact insoluble, right? So this indicating that that's very much going to be true. But again, how much of this salt can actually dissolve in solution, okay? So let's talk about the solubility product constant, or KSP, and something called molar solubility. So as a reminder, the solubility of a compound is the quantity of that compound to dissolve in a certain liquid. We said in Unit 3 that like dissolves likes. That means a polar solute will be dissolved by a polar solvent, and an nonpolar solute would be dissolved by a nonpolar solvent. Now, where do ionic compounds get dissolved by? Well, polar solvents, right? So water is an example. Now, the molar solubility is simply solubility in units moles per liter, And if you guys are paying close attention to that, moles per liter, of course, is molarity, right? So that's moles per liter are the units for molarity, capital M. And just remember, guys, what molarity measures. It's measuring concentration, right? So molarity measures concentration. Now, in terms of calculating KSP, you can do it directly. In terms of calculating the molar solubility, we can use the KSP directly, okay? KSP, of course, is going to be constant at any given temperature. It's the same as if it was a KP or a KC, right, guys? These values are constant at any temperatures. Remember, KSP is still the equilibrium constant, so we're not changing things about it, okay? And so KSP is constant. However, that does not mean the molar solubility is constant. And in fact, the molar solubility of a ionic compound is going to change based on the kind of solution that it's being dissolved in. So that could be different from pure water to a salt solution to an acidic solution to a basic solution. We will talk about solubility again in terms of acidic and basic solutions in Unit 8. Today's video is going to focus on the molar solubility in pure water versus salt solution, okay? So with that all in mind, guys, let's just dive right into an example problem, all right? So it says to calculate the molar solubility of lead 2 chloride in pure water if the KSP is 1.17 times 10 to the negative fifth. And in bolded letters, highlighted in green, I have this warning that it's just a equilibrium problem, okay? So that's good news for us, because if it's just an equilibrium problem, it should be fairly simple to solve. Now, we're looking for the molar solubility. So remember what that molar solubility means. We're looking for moles per liters of lead 2 chloride. And we already know, guys, that that is the concentration of lead 2 chloride. Okay, so that's what we're looking for in this problem. Now, in order to go back to this idea that this is just an equilibrium problem, I first have to write my chemical equation, right? Which is, of course, going to be solid lead 2 chloride is in equilibrium with lead 2 plus aqueous plus 2 chloride ions, which are also aqueous, okay? You'll notice, guys, that when I wrote my dissolution equation here, right, that I made sure to have the proper stoichiometry. That suffices to say that for every 1 formula unit of lead 2 chloride, we're going to, in solution, form 1 lead 2 plus ion and 2 chloride ions. So don't forget to do that. Okay, now it says, guys, since this is an equilibrium problem, right, it says, then that means I'm going to need KSP, right? So our KSP expression, of course, is going to be the product. So lead 2 times the concentration of chloride raised to those stoichiometric coefficients divided by the reactants. Of course, we know the reactants here, because this is a heterogeneous equilibrium. It's a solid. We can't include that in our equilibrium expression. So KSP is going to equal the concentration of lead 2 plus times the concentration of chloride squared. Okay, so we have everything set up, but as this is an equilibrium problem, hopefully everyone knows what we need next, and that, of course, is our icebox. Okay, so we have our icebox here. One thing that we'll note right off the bat is that lead 2 chloride is, of course, a solid, so it doesn't affect this equilibrium. So I can put an X through that whole column. We don't need it. However, you'll notice that if we don't need lead 2 chloride, what's going to happen when we try to get this molar solubility? Well, we just have to see when the concentration of lead 2 chloride is going to equal one of my other 2 ions. And it does, right? We just got done talking about that for every 1 formula unit of lead 2 chloride, it will form 1 lead 2 plus ion. And right there that's how we're going to get our concentration. So if I find the concentration of lead 2 plus, I have found the concentration of lead 2 chloride, which means I have found the molar solubility of lead 2 chloride. So that's exactly what we're going to do. So initially speaking here, there is no lead 2 plus, there is no chloride ions in this solution. Now we're going to solve this icebox in terms of x. So I'm going to add x here. I'm going to add 2x over here. Again, making sure I'm following my stoichiometric coefficients. And at equilibrium, the concentration of lead 2 plus is x. The concentration of chloride ions is 2x. And now I'm ready to plug these values into my my KSP expression. So with that said, we're going to do 1.17 times 10 to the negative fifth is equal to x times 2x squared. If I simplify my right-hand side of the equation, we're going to get 1.17 times 10 to the negative fifth is equal to 4x cubed. Now solving for x, we're going to get x equal, so I'm going to divide both sides by 4, and then I'm going to take the cubic root of both sides. And once I do that, guys, I'm going to get 0.0143 molar. And as a reminder, guys, this value is my concentration of lead, right? So this is my concentration of lead 2 plus. And we just got done talking about how, well, if that's my concentration, it's also equal to the concentration of lead 2 chloride. And what is molar solubility? It is, in fact, just concentration. So my final answer for this equation, folks, is, in fact, the molar solubility of lead 2 chloride is 0.0143 molar. And again, it goes back to that idea of just breaking down the units for molar solubility is in moles per liters. What's moles per liters? That's molarity. What's molarity? It's concentration. And as we can see, the concentration of lead 2 chloride is in fact equal to the concentration of lead 2 plus. What's lead 2 plus? It's X. So therefore, our answer is 0.0143 molar. All right, guys, that's our first example down. Let's go to the next one. Here we go. So it says the molar solubility of silver sulfate in pure water is 1.4 times 10 to the negative 2 molar. I want you to calculate its KSP. So guys, what I want you to do is I want you to pause the video and try to solve this one on your own. This time you're going to do exactly what I just did, but backwards, because you're finding the KSP now. All right, so pause the video and try this one on your own. All right, and I hope you were able to get that the KSP for this problem is 1.1 times 10 to the negative fifth. And as you guys can see, the way that I solved this problem was first writing my chemical equation for the dissolution of silver sulfate, right, which is going to form an equilibrium with 2 silver Ag1 plus ions, right, and then plus 1 sulfate ion that are, of course, aqueous. And then as you guys can see in orange, I completed my icebox table with respect to X. Now, because they gave us the molar solubility of silver sulfate, right, 1.4 times 10 to the negative 2 molar, I was able to easily find the equilibrium concentration of sulfate because that is equal to the concentration of silver sulfate. And as we discussed on the last slide, the concentration of silver sulfate is just its molar solubility. Okay. And because when this particular ionic compound dissolves, it releases 1 sulfate ion. So that's where we get 1.4 times 10 to the negative 2 for sulfate. And then, of course, it releases 2 silver ions. So that's why we had to double it to 2.8 times 10 to the negative 2. Then, guys, I plug that into my KXSP expression, and as you guys can see, we had to square the concentration of silver ion, and then we multiplied that by the concentration of sulfate ion, and that's how we got a KSP of 1.1 times 10 to the negative fifth. All right, let's continue on and talk about how we would interpret a KSP value. The short answer is the same way that we interpret any K value, okay? That means that when KSP is greater than 1, the forward reaction is going to be favored. What does this mean in terms of KSP? Well, that the salt is highly soluble and it will largely dissociate. Okay, so here's an example of one. So we've got sodium chloride's dissolution equation, which is sodium chloride salt is in equilibrium with sodium ion, which is aqueous, plus chloride ion, which is aqueous. It has a KSP of 37.6. We know that means that the products are going to be favored in this case. And what are those products? The aqueous ions of sodium and chloride, respectively. Now, when KSP is less than 1, the reverse reaction is favored. So what does this mean in terms of KSP? Well, the salt is highly insoluble and will largely remain as a solid in solution. So here we've got silver chloride dissolution reaction, which of course silver chloride solid is in equilibrium with silver plus aqueous ion plus chloride ion. It has a KSP of 1.77 times 10 to the negative 10th. And as you guys can see there, it has such a small KSP that the reverse side of this reaction is going to be favored. And well, what's the reverse? The insoluble salt. Okay, back from our solubility rules. So again, KSP is the way that you'd interpret a KSP is the same way you interpret KC or KP, except now, of course, we're just describing it in terms of salt or AKA ionic compound. Okay. Now, in terms of interpreting a KSP value and comparing it from one compound to another, you have to make sure that they have the same dissolution ratio in terms of their stoichiometry. And so what I mean by that is if we were to, I'm going to quickly write all of this dissolution equations for these 4 ionic compounds, and we'll talk about how their stoichiometry is going to allow us to compare them or not to compare them. So let me write them down real quick. All right, everyone. So now that we have the 3 dissolution reactions for these 3 ionic compounds, the only way that we can compare them is if they have the same stoichiometry. So in other words, they have to break apart in the same ratio. Okay, so magnesium hydroxide, if we're looking at it right, is going to form 1 magnesium ion and and then 2 hydroxide ions. So we'll say that that is a 1 to 2 of the ions that it's going to form, right? Then 1 iron 2 carbonate forms 1 ion of iron, plus 1 carbonate ion. So that's 1 to 1. And then our final one is calcium fluoride dissolution equation has calcium 2 plus and then 2 fluoride ions. So that's 1 to 2. So the only if we were to look at their solubilities, we can't compare magnesium hydroxide to iron 2 carbonate. And again, that's because they have different stoichiometry ratios here. Okay. However, we can compare the values of our magnesium hydroxide to calcium fluoride because they have the same dissolution ratio. So in other words, if we're looking at the KSPs here, right, the KSP of calcium fluoride is 1.46 times 10 to the negative 10th. It's a smaller KSP, so that means it's going to be more soluble than our magnesium hydroxide, right? And the only reason, again, that we can compare these is because they both have the same dissolution stoichiometry, 1 to 2, right? And if you look at their molar solubilities, that is indeed true. Calcium fluoride's solubility is 3.32 times 10 to the negative 4th, where magnesium hydroxide is 3.72 times 10 to the negative 5th. So again, in order to compare KSP to relative solubility, they have to have the same dissolution stoichiometry. That means they have to dissolve in the same way. They have to either be both 1 to 1, 1 to 2, 2 to 3, whatever it is, but they both salts or ionic compounds that you're comparing must have the same ratio in terms of our stoichiometry. Okay, let's talk about now the common ion effect, okay? So the common ion effect is a shift in equilibrium induced by an ion common to the equilibrium, okay? So in general, the solubility of an ionic compound is lower in a solution containing a common ion than in pure water. So if you guys recall back to the very beginning of this video lecture, I talked about in this section, we would talk about solubility in terms of pure water versus a salt solution. Well, salt solution is going to be the solution that contains these common ions. So if we have an example here, if we consider our calcium fluoride is in equilibrium with calcium 2 plus 2 fluoride ions, right? That's our equilibrium. And the question is, well, what happens if I add 0.1 molar of sodium fluoride? So what I want you guys to see is I'm essentially introducing a common ion here. So if we were to show the dissolution of sodium fluoride, right, we would end up something like this, okay? And as you guys can see, I now have a common ion in this solution, right? That means I have fluoride here and I have fluoride over here, okay? And because I'm adding 0.1 molar of sodium fluoride, I have now increased the concentration of my sodium fluoride. Well, what does that do? Well, according to Le Chatelier's principle, right, if I increase the concentration of a product, the equilibrium is going to counter me by shifting it towards the reactants. And well, what does that do when we're talking about solubility equilibrium? Well, that means more calcium fluoride solid forms, okay? So in other words, if we have a common ion, it's going to make the ionic compound, you could say it one of two ways. It makes it more insoluble, or perhaps you might want to say it makes more precipitate form. Okay, and that all goes back to Le Chatelier's principle. If you don't believe me, we'll look at an even greater idea now. So Le Chatelier's principle, back from the previous section, is, well, whatever you do to the equilibrium, it does the opposite, right? So if we consider the following equilibrium, we've got iron 2 carbonate is in equilibrium with iron 2 plus ion plus carbonate ion, which are both aqueous. It has a KSP value of 3.07 times 10 to the negative 11. And the question is how will the solutions affect its solubility? So what if we added 0.15 molar of iron to nitrate? Well, guys, I hope you can see that a solution of iron to nitrate is going to have a common ion of iron, right? And if I have a common ion of iron, that means the concentration increases. And as you guys know, according to Le Chatelier's principle, if I increase the concentration of a product, I then am going to shift the reactants, the equilibrium, will shift towards the reactants. So what that means is more iron to carbonate, PPT, or precipitate forms. Okay, and again, it goes back to Le Chatelier's principle. That's how I always like to look at the common ion effect, is I like to apply Le Chatelier's principle because it's just the easiest way to interpret it. Okay, so here's another one. Suppose we add this time 0.15 molar of sodium carbonate solution. Okay, well, I hope everyone can see that we have a common ion here and the carbonate. So if I have a common ion and carbonate, we know that the concentration of carbonate ion is going to increase. And if the concentration of carbonate ion increases, we know, according to Le Chatelier's principle, whatever I do to the equilibrium, it does the opposite. So increasing the carbonate ion, this means the equilibrium is going to shift to the reactants. Well, if it shifts to the reactants, more iron to carbonate precipitate will form. Again, that is the effect of a common ion. Okay, suppose then we add 0.15 molar solution of magnesium chloride solution. Well, in this case, nothing, right? We have no common ion. So no common ion. And that means we're going to have no effect on the equilibrium. Okay. So no common ion, that means we have no effect on that equilibrium. Okay. But guys, when we're talking about the common ion effect, what I really want you to take away from this slide is this idea that the common ion effect is important, or excuse me, not important, but the common ion effect, if you look at it through Le Chatelier's principle, you really don't need to memorize anything special, right? Any additional memorization here. You just need to remember what Le Chatelier's principle is telling us. And of course, whatever we do to the equilibrium, it does the opposite. Just remember, by adding a solution that contains the same ion as what's established in that equilibrium, you're increasing the concentration of it. Well, if we increase the concentration of a product, we know that the equilibrium is shifting back to the reactants. And if we shift back to the reactants, more of our precipitate is going to form as a result of that common ion. So again, you don't need to memorize anything more about the common ion effect. Just apply Le Chatelier's principle. That's all I'm asking you to do. All right? So with that all in mind, I think we need to see the common ion effect and how it would affect the solubility of a solution. So it says, what is the molar solubility of calcium fluoride in a solution containing 0.100 molar of sodium fluoride if the KSP of calcium fluoride is 1.46 times 10 to the negative 10th? All right, so this is, of course, is just going to be an equilibrium problem, which means we need to write the balanced chemical equation. So we're going to have calcium fluoride solid is in equilibrium with calcium 2 plus 2 fluoride ions that are, of course, both aqueous. Okay. And that is our balanced chemical equation, right? And we know from here that our equilibrium expression, right, KSP, is going to be KSP is equal to the concentration of calcium 2 plus times the concentration of fluoride ion squared. Okay. Now, folks, when we're looking at this, we know we're going to need an ice table, right? Because this is just an equilibrium problem. This is nothing special, right? It's just equilibrium problem. So we're going to write our ice box. I'll be right back. Okay, and now that we have our ice box written, folks, we know we're not going to need anything that's in that calcium fluoride section because it's, of course, a solid. Solids aren't represented in our equilibrium expression. And, we know we're starting off with 0 calcium. But the question is, are we starting off with 0 fluoride? And the answer to that is no, because we have a common ion here, right? So we've got fluoride and we got fluoride, okay? And guys, that fluoride is going to tell us, so we got fluoride here, and let me just change this to purple, and we have our fluoride here, right? Well, we know that we have more fluoride initially at the start of this through the respect of that common ion. So at the beginning, we have 0.100 molar fluoride, okay? And again, that's because of the common ion effect. Now we know, because of Le Chatelier's principle, if the fluoride in concentration is increasing, that means we're going to see a shift and that more calcium fluoride solid is going to precipitate, okay? But let's see how this is going to affect its molar solubility now, okay? So at this point, it just is a regular icebox question, which means I'm going to solve this in terms of x. So when I do that, guys, I'm going to add x here, and I'm going to add 2x to my fluoride, okay? So we got x is our equilibrium concentration of calcium 2 plus, And we get 0.100 molar plus 2x for our concentration at equilibrium of the fluoride ion. Now that we have this, we're ready to plug in our numbers into our KSP expression. So we're going to do 1.46 times 10 to the negative 10th is equal to x times the 0.100 plus 2x squared. Okay. Now, I'm about to teach you guys something new here called the x is small approximation. Okay. The reason why, guys, we want to start getting into this idea that x is so small is because the value of many of the KSPs we're going to be working with are magnitudes further away from our actual concentrations we're dealing with, that the change in x is small. Okay, so what I mean by that is if you look at the times 10 to the negative 10 to the negative 10 here, right? Our scientific notation, this value here. And if we compare that to the concentration of our fluoride ion right now, as you guys can see, they are a magnitude of over 1,000 apart, right? So this is over 1,000 magnitude apart here, okay? Now, because of that, guys, because we have over 1,000 magnitude apart between our concentration to the KSP value, we're going to assume that x is negligible. Now, the x that we're going to assume is negligible is anytime x is tied with a plus sign or a minus sign, like right here, that's going to be the quantity we assume is negligible. Now, the reason for this, guys, is because if I add x here, what essentially I'm saying is when you round this to the appropriate number of sig figs, so when you go back to round to 3 sig figs, anything that had to do with a value that's over 1,000 in magnitude greater, when I add them up, based off sig figs, they're not even going to be, they'll be cut off anyway. So that means that x then is negligible, okay? So once we make this assumption, our expression simplifies to this. And as you can see, now I no longer have to worry about squaring this value. And what it's going to save me algebraically, folks, is I'm not going to have to worry about having a cubic, because eventually, if you follow the algebra from this point forward, you'll get a cubic equation. But assuming that change in x is negligible, I now have a one-step algebraic equation, right? Where I'm just going to divide both sides by 0.1, and I'm going to get x is equal to 1.46 times 10 to the negative 8th molar. Okay. Now, for those of you who don't believe me and don't want to assume that x is negligible, if you do expand this out and you do the cubic, and you do get the cubic, and you solve for x once you get the cubic equation here, you will indeed get 1.46 times 10 to the negative 8th. Okay. Now, again, the reason why we can assume x is negligible when we're comparing the KSP value to the concentration we started with, there is over a 1,000 magnitude difference, okay? So therefore, we can assume x is negligible. And when we do that, it makes the algebra much easier. So we're just going to divide both sides by 0.1 molar. And we get x is equal to 1.46 times 10 to the negative 8th. And that, just keep in mind, guys, what this value is. That's your concentration of calcium 2+. But our concentration of calcium 2+ is equal to the concentration of calcium fluoride, because one formula unit of calcium fluoride is releasing one calcium 2+ ion, so their concentrations are the same, which means that is indeed the molar solubility. So our molar solubility of this problem is 1.46 times 10 to the negative 8th. Okay, so that is how the common ion effect would mathematically affect the molar solubility of a particular salt here. All right, guys, and if you were to go back and compare from 2 slides ago where we were looking at the KSP and relative solubility, I pulled off from that slide that the molar solubility of calcium fluoride in H2O, so pure water, is 3.32 times 10 to the negative 4th. Now, as you guys can see, when we put calcium fluoride in a salt solution containing a common ion, the molar solubility is in fact much, much less. So just keep that in mind as we, don't keep that in mind. That is the effect of having a common ion in solution. It decreases the solubility, which means more of that precipitate is going to remain in the solution. Okay, so more solid calcium fluoride remained here. Okay, so in fact, the equilibrium did indeed shift back to the reactants if we're thinking about Le Chatelier. So we're making connections across the board here. All right, let's look at this next slide is going to be more of a conceptual look at the common ion effect. So I want you guys to take a moment and looking at barium sulfate, tell me which of these solutions is it going to have the greatest solubility. So go ahead, pause the video and try this one on your own. All right, everyone, and I hope you were able to correctly identify that the solution is in fact C, sodium nitrate, because sodium nitrate solution is the only one that lacks the common ion. So barium sulfate would be most soluble in solution C. All right, let's keep going. And the final thing we need to talk about is Q and KSP. Okay, that's the final thing we're going to talk about, and then we'll be able to wrap up this video. So as you guys already know, when Q is greater than our equilibrium constant, the reaction proceeds to the reactants. The way that we would say this, though, in terms of these insoluble ionic compounds or salts, I would say that if Q is greater than K, if Q is greater than K as B, then more salt is going to be able to dissolve. If Q is less than KSP, the reaction is going to proceed to the products. The way I would say it for a KSP, though, would be more salt can dissolve or dissociate. And then if Q is equal to KSP, the reaction is at equilibrium, which means the rate of the dissolution is equal to the rate of crystallization. So guys, again, are we changing anything about Q versus our equilibrium constant? No. Instead, we're just talking about how we would describe it differently. So instead of saying that the reaction is going to proceed to the reactants when Q is greater than KSP, I'd say, more salt's going to be able to crystallize, or more ionic compound can form a precipitate, however you want to think about it. Let's dive in and do an example problem now. So this says, will a silver sulfate precipitate form when 50 milliliters of 0.050 molar solution of silver nitrate is mixed with 75 milliliters of a 0.0050 molar solution of sodium sulfate? The KSP of our silver sulfate is 1.5 times 10 to the negative 5th. Well, we're asking here if a salt will precipitate, right? So that's what we're asking. We're trying to find this silver sulfate, is it going to precipitate? So in order to determine whether or not something's going to precipitate, we need to find Q, right? So ultimately, we're looking for Q. And again, the reason why we're looking for Q, because if Q is greater than the KSP, okay, we know that the ionic compound will form a precipitate. Okay. Now, if Q is less than the KSP, more can dissolve. And then finally, if Q is equal to the KSP, right, we're at equilibrium. Okay, so that the rate of dissolving is equal to the rate of the rate of crystallizing. Okay, so with all that in mind, that's the long worded version of saying that we have to find Q, right? So in order to find Q, we of course need a balanced chemical equation. So we're going to have silver sulfate solid is in equilibrium with 2 silver ions that are aqueous plus 1 sulfate 2 minus ion, which is also aqueous. Okay, and that means my value for Q is going to be my products. So silver ion 1 plus raised to its stoichiometric coefficient times the concentration of sulfate raised to its stoichiometric coefficient, which is a 1. So, of course, that's why we're not writing anything. And, guys, you'll notice that Q is written the same way that we would write KSP because, well, Q is defined that way, except that we can calculate Q at any point of this reaction, right? So, Q we can calculate at any point. The KSP, of course, can only be calculated at equilibrium, okay? So, now that we know what we need in order to calculate Q, right? We need silver ion and we need the concentration of sulfate ion. Okay, so let's set this equal down here. So we need to find the concentration of silver ion, and then we need to find the concentration of sulfate ion. Now, guys, you'll notice that we're adding these solutions together, right? So we're adding 15. We have a solution of 50 and 75 milliliters being added together. So we have 50 mils being added to 75 mils. And the reason why I'm bringing this up is because it's not just that easy to look at the concentration of our silver nitrate and our sodium sulfate respectively, right? Because, oh, they gave us the concentrations. We're able to just plug these values in right away and get our number. We can't because they're liquids and we have a new total volume now, right? Because we added 50 milliliters of one solution to 75 milliliters of another, which means our new total volume is 125 milliliters. So because we have this new volume of 125 milliliters, we have to go recalculate the concentration of silver ion and sulfate ion. So how do we do that? Well, we got to first find in order to find concentration, just remember what it is the concentration is moles per liter. So I have to find the moles of silver, and I have to find the moles of sulfate, and then divide by 125 milliliters, which is 0.125 liters. So that's ultimately what we're going to do here. So looking at our first solution here, in order to find the concentration of silver ion, we've got 50 mils, right? And I got to convert milliliters into liters, so I'm going to divide by 1,000. Okay, and that's 1 liter on top. And 1 liter on the bottom is going to be 0.5 moles of silver nitrate. Okay, and if we look at our dissolution, right, so 1 mole of silver nitrate is going to equal 1 mole of silver. So in other words, for every 1 mole of silver nitrate that would break apart, it would form 1 mole of silver. And guys, when we do this, we get 0.0025 moles of silver ion. Okay. And guys, I'm going to do, and now in order to get its concentration, what I have to do is divide by 0.125 liters. So let's do that. And when we divide by 0.125 liters, we get a new concentration of 0.020 molar. And that, of course, is our concentration of silver. Now, guys, I'm going to do the exact same math for sulfate, except that I'm going to pause the video and the math is going to appear. Alrighty, so as you guys can see, my stoichiometry, or rather, in order to find the concentration of my sulfate ion, you now see the stoichiometry. You'll notice, guys, that I started with 75 milliliters, and the moles of sodium sulfate is different because, of course, it's different volume and molarity as per the question. So that's why those numbers are different. But nonetheless, the stoichiometry appears the same, right? Where we first went from milliliters to liters, liters to moles, and then moles to moles. And then finally, at the end, we divide by the new total volume, which is 0.125 liters. And now we have our concentrations of silver and sulfate, respectively. When we plug those numbers into our Q equation, right? So if we go back to the top here and we plug these numbers into Q, so Q is going to equal 0.020 squared times the concentration of sulfate, which is 0.0030. Our Q value is going to equal, one moment, let me calculate this out, 1.2 times 10 to the negative 6. Okay, so 1.2 times 10 to the negative 6, so that means Q is greater than, or excuse me, Q is less than K. So is this going to form a precipitate? No. No PPT, no precipitate forms. Instead, what's going to happen is, according to Q, more Ag2SO4 can dissolve. Okay, so our answer here is in fact no. Okay, and not only that, not only is our answer no, but according to Q, right, so Q is less than our KSP, indicating that more silver sulfate is actually going to dissolve. And with that being said, guys, that's the end of today's video. If you have any questions, shoot me an email.